The vacuum diode described in the last video was eclipsed by the semiconductor diode. To understand how this works, we must first take a look at semiconductors themselves. After all, they are the basis of just about all of modern electronics. And it's not an exaggeration to say that they are the foundation stone on which a modern world is built. As we've discussed in previous videos, in an insulator, all electrons in the atom are tightly bound to the nucleus and are not free to move. In a conductor, however, they are much more loosely bound and are free to move. We say that they are charge carriers. Semiconductors come in between insulators and conductors on the periodic table. Although they normally act like insulators, their electrons can easily gain enough energy, for example through the addition of heat, to free themselves from their parent atoms and become available for conduction. Although it wasn't the first one used, and it certainly isn't the only one, I'm going to restrict this discussion to silicon, because it's a king of semiconductors. Silicon is to electronics what carbon is to life. Firstly, it's extremely common. It's the second most common element on Earth and the 8th most common one in the universe. Secondly, it's non-toxic and easy to handle. Thirdly, when heated up in oxygen, it forms SiO2, silicon dioxide, which we know as quartz in its crystalline form and as glass in non-crystalline form. This is an excellent natural insulator. Fourthly, if you react it with nitrogen, it forms Si3N4, silicon nitride, which is nearly as hard as sapphire, and in fact silicon carbide is even harder. These fortuitous natural properties, along with its electrical ones, make it absolutely ideal for electronics. Silicon atoms form 4 bonds and can form giant crystals, which are the base material for modern electronics. These crystals are a 3-dimensional structure, but are shown here in our diagrams as a flat 2-dimensional one for convenience. Pure silicon in this form is sometimes called intrinsic. Intrinsic silicon is basically an insulator and has a resistivity of about 230 kiloohms per centimeter. However, for use in semiconductors, silicon is usually doped. Doped silicon has impurities deliberately added to it. If an element immediately to the right of silicon in the periodic table, like phosphorus, is added to it, it bonds into the silicon crystal structure, but has an extra electron because it has 5 electrons in its outer shell. 4 of them bond to the silicon atoms around, and the 5th one is free. This free electron can then carry a current. We say that the electron is a charge carrier, as previously mentioned. We call this type of doping N-type, and the silicon generated N-type silicon because of the negative electron. Likewise, if an element to the left of silicon in the periodic table is added, for example boron, which has 1 electron less in its outer shell, then we would leave a vacant bond. This is called a hole. Now the hole is of interest because an electron can jump into it from an adjacent atom. And of course this leaves a hole in the atom that the electron has jumped from. And so the hole moves to the right hand side. But because it's a lack of electron, it acts and looks rather like a positive charge. We therefore call semiconductors with holes like this P-type material, because they appear to have positive charges. Doped semiconductors like these are called extrinsic, and there's a couple of other things to notice about them. Firstly, the amount of doping added is tiny. For a weakly doped material, it's only 1 impurity atom per billion of silicon, and for a strongly doped material, it's about 1 atom to 1,000 of silicon. Secondly, holes generally move more slowly than electrons. We say that they have a lower mobility. The main charge carrier in a material is called the maturity carrier. However, defects in the silicon crystal, thermal excitation, or contamination might mean that a few free electrons are also present in a p-type material. And similarly, some holes might be present in an n-type material. These are called minority carriers and are generally something which we are trying to avoid.